Welcome to my CCNA Security version 2 lecture review. Here we're looking at chapter 8, implementing VPNs. Alright, with that said, our chapter is broken down into 4 key areas: VPNs, IPsec VPNs, components and operations. Looking at site-to-site, we will talk a little bit about mobile VPNs as well, and we'll end with a summary. So again, 8.1 is focusing on VPNs. Once we are finished with this lecture, you should be able to describe what VPNs are, their benefits, and compare and contrast site-to-site versus remote access VPNs, commonly called mobile VPNs. Alright, so 8.1.1, VPNs. Some of this is going to be controversial. Cost saving, security, scalable, compatibility. I really wouldn't say VPNs really help reduce costs, but they can depending on how you implement them. I work for a large institution where we could have dedicated path-to-path between locations, and that's expensive. Or we can connect to the internet, and through the internet use a VPN to tunnel securely. In that regard, we are saving money by doing that. Typically, VPNs are secure as they encrypt data and as they flow through a third-party network. They can be scalable depending on how you implement them. And they could be compatible. Again, ignoring the underlying technology, VPNs should work through any network. Any layer 2 network, VPNs typically don't care. Alright, so since I said layer 2 VPN, or since I said layer 2 doesn't really care, normally IPsec VPNs operate at layer 3. They deal with the IP section portion of it. And you can have a layer 3 IPsec VPN through the internet, and again, this operates at layer 3. I know I said layer 3 several times, but it's important to understand that different VPN technologies operate at different layers. There is a layer 2 MPLS VPN, which is different from a layer 3 IPsec VPN. So keep that in mind. 2 types, remote access and site-to-site. Site-to-site typically is with each location having a static address, and they do not change. Where a mobile user with a laptop connecting anywhere in the world will have a dynamic address. Typically, their IP will continuously be changing depending on their location. However, they will be tunneling to a location that is static. So in this example, we have a laptop connecting back to headquarters. Headquarters IP should be a static address. So no matter where you are globally, you should be able to reach that address. Components of remote access will be a network to connect through, a home base per se, headquarters, data center, something with a static address you'll be connecting to, and a mobile client with network access. Typically in this regard, we're talking internet access, so you can tunnel through the internets. With a site-to-site VPN, it's going to be 2 routers, one on each end, connecting through the internets. The individual clients on either side will not know they're connecting through the internet, will not know that the resources they're trying to access are on a different network through the internets. It will act as if they're all part of the same LAN. Okay, there's some arguments there. Some people could say, well, there's going to be a different network as you travel through the internet. But yes, that is true. However, in this simplistic view, we're looking site to site. The actual computers that are going to be using the VPN should not have any knowledge that they're the VPN tunnel. That's all going to be done at layer 3. So the layer 2 devices, broadcasts, and such should be allowed to access through the VPN. And again, the VPN will have typically an ACL that directs traffic through it for layer 3. Alright, moving on. Section 8.2, IPsec. IPsec is one of the most common types of secured VPN out there, and this is the type of VPN technology you should be using. There are numerous types, but IPsec is by far the most secure at the time of these recordings. In this section, you should be able to describe IPsec protocols, basic functions, compare AH and ESP protocols, describe IKE for key sharing as well. Alright, so introducing IPsec. IPsec actually really pushes the IPsec framework, which is the protocols, confidentiality, integrity, authentication, and the appropriate DH or Diffie-Hellman group for key exchange. So IPsec protocol, we have things like AH, ESP, and a combination of the two. For confidentiality, we have integrity. For confidentiality, we have their encryption types. For integrity, we have hashing. For authentication, we have things like pre-shared key. And Diffie-Hellman, we have DH groups. We're going to explain these here in a few slides, so just bear with me. So the nice thing is when we're talking about the IPsec framework, you have to realize that when we're doing a site-to-site tunnel using IPsec, you have to have it set up the identical in both ways also. Alright, so let's talk about confidentiality. Confidentiality should take a key plus an encryption algorithm, and that should change it to ciphertext. Something that is not easily readable. Shouldn't really be readable at all. And then you need the key and a decryption algorithm to actually take the ciphertext and make it readable again. Now the keys can come in two forms. Both keys can be identical, that's symmetrical. Or you can have one key for encrypting and one key for decrypting, that's asymmetrical. And I know we don't really talk about cryptography in these video sections, but I have other videos about cryptography if you want to know more. There are, at least in this slide, 4 common types of symmetric cryptography encryption types: DES, triple DES, AES, and SIL. AES is the most commonly acceptable. SIL is newer and supposed to be more secure, but you at least want AES. While many organizations still use triple DES is extremely easy to break into. So again, AES or above are the preferred methods. Alright, let's move on to integrity. We have hashing algorithms. A hashing algorithm allows us to take a message, to run it through a algorithm, and it will generate a fixed length. So if we send the message and the hash, and the recipient gets it, takes the same message and runs it through an algorithm, the same algorithm, the hash values should be identical. That way you know if the message was altered. Two big ones are MD5 and SHA, typically SHA-1 or SHA-256 or SHA-512, or there's lots of SHA versions. But MD5 and SHA-1 are the two big common ones. They have different bit lengths. MD5 has 128 bit, where SHA-1 has 160 bit. And again, you use this for message verification. You can always take an object, hash it, send the object with the hash value, and the recipient can always verify that they are truly receiving what you sent them. Hashes are one way, so you should not be able to decode a message with just a hash. Just keep that in mind. Moving on, authentication. Authentication is about being able to share the keys PSK is pre-shared keying. That's a common way of looking at the authentication key plus ID information, having it hashed, sending it through the internet, and having it being able to compute the appropriate hash as well. Here, we are typically using the same pre-shared key to verify. RSA is another type of key encryption, but they focus with digital certificates as well. And again, you'll notice here, authentication plus ID, hash. Hash will be fed into an encryption algorithm with a private key, and that will be sent through a digital signature, and then that gets sent over. The remote option will be the authentication key, the ID, hash. The digital signature will have to go through a decrypt algorithm for a decrypted hash, and we will compare the computed hash and the decrypt hash to see if they are equivalent. For the decryption algorithm, it will use a public key. Notice here, public versus private key. That's going to be asymmetric key systems. And that's how you can verify if the keys used are the appropriate keys. And then, are the users authenticated based off those key values? So how do we make sure that the key exchange is secure? Diffie-Hellman is the process that allows this. There are several DH groups. DH2, 5, 12, 14, and 15 are common ones. This is about key exchange. The functionality isn't really important. The important part here is whatever you go on one side has to be identical on the opposite side for key exchange. Alright, let's get further into the more nitty-gritty of IPsec. Here we're looking at IPsec protocols. At the top layer, AH versus ESP versus a combination of both. AH is authentication header. All data is pretty much in plain text. It does provide integrity, authentication, and a key exchange. The AH takes the IP header plus the data plus a key, generates a hash, and then you end up with the IP header, the AH, and the data. So the peer router will compare recompute hashes to a received hash for verification. If they are identical, then we know that no bits were modified in transit. So it provides greater integrity. ESP, encrypted payload, actually focuses more on confidentiality, integrity, authentication, and key exchange. So here, we are actually looking at the IPHD and the data and an ESP trailer. That will be encrypted, and then the ESP header with the encrypted packet can also be authenticated. And it will then apply a new IP header on top of it. That way, it's not just the header information that is protected, but it's the entire thing with the payload being encrypted. There are two types of modes when we're talking ESP and AH. We're talking transport mode. That is looking at the data and ESP trailer being encrypted, and tunnel mode. With tunnel mode, we're looking at the original IP header, the data, ESP trailer being encrypted, and attaching a new IP header at the very beginning for verification or authentication. Tunnel mode is going to be more... The important part here is tunnel mode protects the internal routing information by encrypting the IP header of the original packet. Transport mode encrypts only the payload so that the IP header of the original packet is not encrypted. So there are some differences between the two. Moving on is key exchange. over the internet. So again, here we have the IKE Protocol. We have our IPsec Protocol, CIA, and DH. IKE will help negotiate between the SA peers. How is that done? It's typically done in 2 phases. Phase 1 for VPN will negotiate the key mapping policy for creating the tunnel. It will negotiate the appropriate policy for encryption, for what type of encryption technology. Here they're using AES for the appropriate type of hashing, authentication protocol. Here we're using pre-shared key, the appropriate key exchange. Here they're doing DH14. That would help to negotiate the appropriate policy. Once that is done, the DH key exchange will then exchange keys. Once that is done, verifying the peer identity is done. That completes the 3 main steps for phase 1. Once that portion is done for the key exchange, phase 2 comes into play, and that will negotiate the IP policy for sending secure traffic across the tunnel. So phase 1 helps to build the tunnel. Phase 2 focuses predominantly on the type of traffic that will be sent through the tunnel. Here we have negotiating the IPsec security parameters between 2 routers. One of the last major sections is implementing site-to-site IPsec VPNs through the CLI. We're going to go through the process of setting up our tunnels. This chapter we're looking at describing the IPsec negotiation and the appropriate 5 steps for configuration, configuring the ISAKMP policies, the IPsec policies, applying a crypto map, and then verifying functionality. So this is actually going to be one of the larger sections of this chapter. Alright, so with that said, first section is going to be configuring a site-to-site VPN using IPsec. Again, we have 5 main steps. We have setting up the hosts, setting up the connection, response. So, with that said, IPsec negotiation, step 1. Host A should send an interest traffic to host B. IPsec VPN negotiation should start happening. Step 2. R1 and R2 should negotiate the IKE Phase 1 session. That's the three steps we've already discussed. That will then in turn negotiate an IKE Phase 2 session. So Phase 1 should be getting up the sharing of the keys, pretty much getting up the majority of the tunnel. Session Phase 2, within that session, should focus on what traffic is allowed to go through the tunnel. Next, step 4, the information is exchanged via the tunnel. Should be done encrypted. And then the last step, the tunnel is terminated once no longer needed. You can have the tunnels kept alive so they're always active if you want. That's a little later in this chapter when we discuss it though. So again, here we have one site through a common network, tunneling through that common network to a secondary site, thus being able to protect the data as it flows through that common network. That common network we're discussing typically is the internet. Alright, so we have to set up a few policies. First of all, what type of encryption are we using? What type of authentication are we using? How are we exchanging keys? What is the tunnel life? And what type of protocol will the tunnel use? So, in order to figure out how to encrypt the traffic, we're setting up and configuring the ISAKMP policy for Phase 1. When we're talking about authentication, that's going to be part of phase 2. When we're talking about the key exchange, we're configuring a crypto map for that. When we're looking at the ISAKMP tunnel life, we're looking at IPsec policies. And lastly, when we're looking at the protocol for the tunnel to use, we're verifying the IPsec tunnel operations just to make sure that it is being maintained. It's broken down into those 5 steps so that we can actually look through the appropriate CLI commands so we can figure out how to configure those items as necessary. Alright, so how do you permit the appropriate traffic? Well, that's ACLs. So here, if we're looking at 3 types of ACLs, one is going to permit the ISAKMP traffic. That's going to be UDP. So it's going to be a standard ACL. UDP is the protocol, and equaling the ISAKMP ports. And if we're looking at ESP type traffic, we have to permit ESP, as that's going to be the protocol. If we're permitting AH traffic, again, now it's going to be the AHP for the protocol. ACLs are important here because we have to know what type of traffic to match to send through the tunnel. Here we should be matching the traffic to send. Here we have the appropriate ACLs. It's a named ACL. We permit the IP, we permit ICMP, and then we permit the appropriate 3 ISAKMP, the appropriate ESP and AH protocols, and we deny everything else. Then we apply it to an interface. So with that said, we're going to start introducing what's called a GRE tunnel, which is a little easier to set up. And it basically takes the original packet and it creates a GRE packet instead. Not quite sure why we put it there, but Cisco decided that was a good spot for it for some reason. So moving on, we're talking about the ISAKMP policies. If we want to see the default policies, we can show crypto ISAKMP default policies. That will let you know the appropriate default options. If we want to verify or configure a new policy, we can actually do a crypto ISAKMP policy. You give it a number, and then you can set the appropriate commands. Here we're setting a policy of 1. We're setting the hash to SHA. We're setting the authentication portion to pre-shared key, PSK. We are setting the DH group to group 24. We're setting the lifetime. We are setting the confidentiality, aka the encryption type, to AES to 56-bit. And that's it. How can we verify our policies? We can do a show crypto ISAKMP policy, and that will show us the values for our policy. So now that we discussed some of the commands, and now let's get into the crypto ISAKMP commands. Here we need to be able to set up our new key, our key string, and our peer addresses. We can do what's also the key string or host name if DNS is functioning. Here's an example of the configuration for our key on R1 and for R2. The top screen is R1, bottom screen is R2. As you see, we're setting our crypto ISAKMP key and our peer address. So on R1, we're giving it our peer, our router 2 address, and on router 2, we're giving it a key and our peer, also known as R1 address. So moving on, we have our actual policies. So if we're looking at discussing the phase 1, we could do a show crypto ISAKMP essay. That will show us the appropriate tunnels for phase 1 if they exist yet. In this example, nothing currently exists, so nothing is currently there. We have to configure an ACL to define interesting traffic. Basically, what traffic is allowed to go through the tunnel. So we have to make sure on R1 we set up the ACL for the appropriate source and destination. And on R2 we have to have the reverse. Basically, you want to be able to say if the destination is this network, we're going to be sending it through the tunnel. And that's what this ACL really does. Again, we have to apply it and then we have to map it so that when the matching addresses are found, we know how to route them. And we should be routing them through our VPN tunnel. If we're looking at how to look at our transform set, we actually have the ability to set up the AH or ESP and then the appropriate sub-options if you would like. Here we are doing the transform set ESP AES, and we're also doing ESP SHA. And again, protocols have to match on both sides. You have to make sure to set a transform set. This defines the protocols we're going to be using. Alright, so now let's move on to setting up our crypto map. Our crypto map will be given a name, a sequence number, the appropriate IPsec, whether it's using ISAKMP or manual. Alright, so map name will identify the crypto map sets. The sequence number will be the sequence number you assign to the crypto map entry. And then here we're looking at IPsec ISAKMP, which will indicate that IKE will be used for IPsec. If you do IPsec manual, it will indicate that IKE will not be used to establish the appropriate IPsec essays. So again, kind of depending on how you're going to be doing it. For most of our labs, we're using IPsec ISAKMP option so that it will use IKE for sending data back and forth. And you'll see this in our labs that will kind of reinforce the commands. As an example, here we're setting up our crypto map. We name it. We're giving it a number 10, and we're doing the IPsec ISAKMP for auto. This will set up a new crypto map, and then we can actually do subcommands to kind of match options. Here we are matching addresses 101. That's actually a ACL. We set the transform set, we set the peer, we set the DH group, we set the appropriate security associations with lifetime, and we have to match them again on both sides, and then that should help the tunnel build. If after all of that, once you actually set them, you should be able to do a show crypto map to see that the tunnels are actually up and functioning. However, one of the things that we have to worry about is when we do this, we also have to make sure to apply the crypto map to an interface. That is the only way for the tunnels to actually come up. We do that by navigating to the interface and applying the crypto map to the interface. That actually enforces the interface to match traffic using that crypto map. That is actually one of the biggest things that I've seen for failure, is they will do all of the mappings, but they won't apply the map to an interface. So keep that in mind. Alright, one of the last major sections in this group is talking about IPsec VPNs. So this portion deals mainly with verifying traffic actually is being sent through the tunnel. And you can do that via sending a ping. And you can actually do it from the router by doing a destination and source to verify. You can also do a show option, show crypto ISAKMP assay, and it'll show source and destination. And it should show the state of the map and the state of the tunnel, which in this case it should be active. You can also look at the show crypto IPsec assay, and it should show you the interface, it should show you the local address, the peer, and all the additional details. And that is this chapter in a nutshell. One of the fun parts with this is it may seem like a whole lot, but once you're actually programming this in the lab, you'll see that it is a lot easier to actually memorize and maintain by going through several of the labs. If you have any questions or concerns, please reach out, and I'll try to get those answered as quickly as I can. I want to thank you.